soundness is this basic canonical theorem that we all prove about our type systems. It's like PL'101. We teach this to students in the first year, and many papers on type systems conclude with a triumphant statement of type soundness. So for many people, type soundness is the thing you prove about your type system. And you're probably wondering, what can I possibly tell you about type soundness that you don't already know? So I'm going to make a long story short, what I'm going to argue in this talk is that the type soundness theorem that, as it is commonly understood, the type soundness theorem that you already know how to prove is not strong enough in a sense that I'll make very precise. And I'm going to argue that we should be proving a stronger type soundness theorem, and I'm going to show you how to do it. But before I get there, let me begin by just reviewing the common understanding of what type soundness means. So type soundness, or type safety as it's often called, was proposed originally by Robin Milner in his classic 1978 paper, A Theory of Type Polymorphism in Programming. And this is one of these amazing papers that's under 30 pages and yet manages to introduce ML polymorphism and principal type inference and type soundness, which is characterized by the famous slogan, well-typed programs cannot go wrong. Now, of course, Milner didn't actually literally mean that well-typed programs can't go wrong, because we all know well-typed programs can go wrong. But what he meant was that well-typed programs have well-defined behavior. Okay, so if they do go wrong, they go wrong in a way that is well-defined according to the semantics of the language. Now, he defined his semantics, and he characterized this undefined behavior using a denotational semantics which had a special wrong value. And if you had, for example, if you tried to have a program with an integer that is applied like a function, that would have the denotation wrong. This is not how we typically formalize well-defined behavior now. Instead, the predominant means of doing that is through the syntactic approach to type soundness that was pioneered by Andrew Wright and MPI-SWS in their seminal paper of 1994. So they did a couple things in this paper. One of them was to reformulate the whole setup using a small step operational semantics instead of a denotational semantics. And then they characterized what I'm calling undefined behavior here as getting stuck during the execution of a program at some intermediate state. And so they showed that well-typed programs can't get stuck. That was their formulation of the type soundness theorem. Now, the way we typically prove this now is actually using a slight refinement of the Wright-Felleisen proof method due to Bob Harper, which has come to be known widely as progress and preservation. And the idea behind progress and preservation is extremely simple. So I'll just review it quickly. The basic thing is you want to lift the notion of well-typedness from programs to machine states, so it's a well-typedness on machine states. And then you prove two theorems that sort of work hand in hand. One of them is progress, which says that well-typed programs can always, well-typed machine states can always make progress to some future state, or else they're in some valid terminal state. And preservation says that well-typedness of machine states is preserved throughout execution. And these two things together give you that well-typed programs can't get stuck. So I think this is all probably familiar to you. And before I start complaining about syntactic type soundness, I want to first just make clear what is really good about it. So the thing that's really good is it's an extremely simple technique, and much simpler than any of the techniques that had come before. It's easy to teach to people, and it scales to handle many useful features you find in real programming languages that are potentially more difficult to reason about. Things like mutable state, concurrency, subtyping, you name it. So that's in the positive side. So what I'm going to talk about today is that type soundness has several, or syntactic type soundness in particular, has several major, in my opinion, limitations that prevent it from really scaling to a technique that works for real languages. And I'm going to basically isolate two of these limitations. The first one has to do with data abstraction. So one of the major functions of type systems is to support data abstraction, to provide data abstraction mechanisms, things like closures, objects, ADTs, modules. And what these mechanisms do is they allow the implementer of the abstraction to hide implementation details from clients. And why is that important? It's important because it means that the implementer can impose invariance on the private data representation of their abstractions. And the problem with syntactic type soundness is that it says nothing about data abstraction. It doesn't really tell you whether the data abstraction mechanisms in your language actually work. So to illustrate this, I want to go to a concrete example, which I'll use as a motivating example throughout the talk. And to just fix the language that I'm talking about, I'm gonna use this language I'm calling mylang. Any similarity to ML is purely coincidental. Because ML is machine learning, Anyway, so this is mylang. So there's actually that screen is slightly off. I don't know if someone in the back can fix that screen, but okay. Yeah, maybe you can look into it, Ranjan. I just noticed. Anyway, so yes, this language has higher order functions, products, base types, abstract data types, which are represented using existential types, general mutable references in the style of ML, so that means mutable references to things of arbitrary type, and concurrency. So here's the example. So this is an example of an abstract data type or an ADT representing symbols. So the symbols here are represented as an existential type. This ADT is represented as an existential type where the alpha, the abstract type that's bound in the existential on the bottom, right here, represents the type of symbols. And then there's two operations for reasoning about symbols, for manipulating symbols. The first one is a gensim function. So this is a function that allows you to generate fresh symbols. Every time you call it, you get a fresh symbol. And the second function is this is just a simple example. It's a checking function, okay? It's going to check that the symbol that's passed into the type alpha is a valid symbol. Now, our expectation in this particular example is that all symbols of type alpha are valid symbols, so this function should always return true. Okay, that's going to be the behavior we expect. So now, looking at the code itself, the idea is we're going to represent the abstract type of symbols internally with the type int. So symbols are just integers. And the way we guarantee a steady supply of fresh symbols that are distinct from the previous ones is using mutable state. We use an integer counter c, which is initially set to 0. Okay, and then how do we implement the functions? Well, the gensim function is going to be implemented using an atomic fetch and increment operation. So every time you call it, it's going to do this fetch and increment, go from initially it'll return 0 and then 1 and then 2 and then 3, etc. And it'll keep bumping up the counter every time. The checking function is correspondingly going to check an invariant that is maintained by this code, which is that the symbol that's passed into the checking function, s, must be less than the current value of the counter. And that's intuitively because the invariant that's getting maintained in this ADT is that the only symbols of type alpha that have been produced at any point during the execution of the program are those natural numbers that are less than the current value of the counter. Okay, so that's the expectation about what this code does. And the reason we can expect that is precisely because of data abstraction, right? The closures in this code hide the access or mediate access to the counter C, and the existential type hides the definition of the symbol type. So the check here should always return true when you link this code with arbitrary well-typed code. But syntactic type soundness does not guarantee that. And to demonstrate that syntactic type soundness doesn't guarantee that, I'm going to do something a little funny, which is to extend mylang with a rather suspicious-looking primitive, which I'll, for lack of a better word, call covfefe. So here's the semantics of covfefe. Okay, so covfefe is an expression of type unit, and it has two rules for its dynamic semantics. The first rule is basically saying it could just be a no-op. Okay, that's the rule on the left. And this is, by the way, just a standard heap-based semantics for mutable state. However, what it could also do is it could find some location in memory, non-deterministically pick some location L that is currently storing an integer n doesn't matter, and it'll set the contents of L to 0. Okay, so those are the rules of covfefe. So obviously this is a stupid primitive, right? It's just for purposes of making a point. So the point that I want to make is that first of all, covfefe is syntactically perfectly sound. Okay, it's trivial. It's a trivial exercise. You can go do it when the talk is over to prove that this is a syntactically sound extension to mylang. Because first of all, clearly covfefe can make progress. The rule on the left guarantees that. And as far as preservation is concerned, it may just replace some integer in memory with another integer. So that again doesn't affect type soundness. So this will never cause well-typed programs to get stuck. But as you can probably imagine, this is a very, very bad primitive. So to demonstrate that, let me look at this client of the symbol ADT that uses covfefe. So here's the client that's unpacking the symbol, the symbol ADT I defined on the previous slide. It gives names for the abstract type and the gensim and the check functions. It calls the gensim function once, producing a symbol s. Then it does this covfefe, and then it checks that s is still a valid symbol. Okay, and you can probably guess what's going to happen here. So first of all, when we evaluate symbol, we get the counter is initially 0. When we do the gen sim, the counter gets bumped up to 1, and the symbol gets returned. The symbol that gets returned for S is 0. Then when you do covfefe, one possible behavior is that the counter gets set back to 0. And so when we now try to check that the symbol is valid, that's going to try to check that S is less than the contents of the counter, which is false. So the check has now failed. So this is basically, this primitive, while being perfectly syntactically sound extension to the language, has completely violated our reasoning about data abstraction. So as I said, this is a contrived example for purposes of illustration, but actually it's not really, because covfefe is really just Java-style reflection. This is just an exaggeratedly awful version of that has no useful computational meaning. But that's really all it is, okay? And something you may not know, actually, is that in Java 9, the most recent version of Java, there is finally support for opting out of reflection. So only now can you actually define classes that cannot be reflected on. And in fact, if you read about Java 9, then you read that that's considered a major win for strong encapsulation. But how do you actually prove that Java 9 is actually an improvement in any way on its predecessors, right? If all you have is syntactic soundness, then there's no difference. So that's my first limitation I wanted to point out. The second one has to do with unsafe features. So many real programming languages, including many supposedly safe programming languages, have unsafe features, unsafe escape hatches. I'm thinking of things like obj.magic in OCaml, unsafe perform.io in Haskell, and unsafe blocks in Rust. And these features serve a very useful purpose. They're widely used in many libraries for purposes of performance, but also for purposes of functionality. Sometimes there's things you simply can't implement in the safe fragment of your language, and you need to dip down into some lower level of data representation in specific ways. And so these features serve a very important purpose. But the problem is syntactic type soundness has nothing to say about them. Okay, because as far as syntactic soundness is concerned, it's a theorem that only applies to the safe fragment of your language. So effectively, what that means is, as far as syntactic soundness is concerned, these languages in their totality are no better than C or C++. And that's not true. Okay, we know that's not true. We program in these languages. We do get safety guarantees, and so at least in practice, right? And so how could we figure out what those safety guarantees are? So the reason I claim that these languages are better is because the way you use unsafe features in these languages is that you don't just program willy-nilly with them. You use them in safely encapsulated ways, or at least that's how you should. So here's a picture of how people typically try to use unsafe features in a safe language. Most of their code in the language is written in the safe fragment, but then they have libraries that internally make use of unsafe features. For example, here's a little snippet of some code from the refcell library in Rust, which is using unsafe blocks. But these unsafe features are encapsulated by safe APIs. That's what the green pentagons there are denoting. The claim that the developers of these libraries want to make is that these safe APIs are basically an extension, a safe extension to the underlying safe language, so that no well-typed client of the libraries that doesn't use unsafe code themselves will ever observe any undefined behavior. Okay, so if all the unsafe code in the program is restricted, it's confined within these libraries, you should never observe any undefined behavior. So if this claim is true, that's clearly a big win over languages like C or C++, where there's no similar way of confining the use of unsafe features. But the question is it actually true, or how would you even go about proving that this claim? And I want to emphasize at this point how non-obvious this is by giving you relating a brief cautionary tale. So last year at POPL', Aaron Turan gave a wonderful keynote about the Rust programming language. This is a language we've been studying in this work. And Rust is a language that's been developed in Mozilla in the past several years that's intended as a safe systems programming language, a safe alternative to languages like C++. And so a couple years ago, in 2015, a few weeks before the 1.0 release of the language, he wrote this blog post, which has been heavily cited, called Fearless Concurrency with Rust. And what he did in this post was show how this picture that I showed on the previous slide, the safe core language with all these libraries that extend the expressive power of the language in interesting ways, was really a source of a unique selling point of Rust. And he explained a number of different libraries and all the cool things they do. And he built up to an API called scoped threads. And scoped threads is an API that allows you to actually spawn threads that have access to the parent thread's stack frame. This is something that's very hard to do in most safe languages. Unfortunately, the fearless concurrency here was a little too fearless, because on the same day that he wrote this blog post, a soundness bug was found in Rust involving the scoped threads API, and which led to much gnashing of teeth. So this is the if you're interested in reading about this is the article I recommend reading. Just Google for Leakpocalypse. And I'm not going to go into the details of exactly how what the soundness bug was, but the point I want to make was actually it was a particularly insidious bug because it involved an interaction of two libraries, two APIs, each of which was safe on its own, but when put together, you could get use after free errors. And so this was something where this was a number of smart people were involved in producing these libraries and hadn't figured this out before. It was a little embarrassingly late. So the question is, how can we ensure formally that such soundness bugs like this don't occur? Is there any way, syntactic soundness doesn't give us any help because it rules unsafe features out of scope, out of consideration. Is there something else we can do? So before I go on and tell you what is the something else we can do, I want to just make an important point, which is that these two limitations I presented, they seem superficially very different. They're really the same thing. They're really both about the fact that syntactic type soundness doesn't tell you anything about data abstraction and encapsulation. Right? It doesn't tell you anything about whether the abstraction mechanisms of types are actually doing their job. And to make that point, to drive that point home, I want to go back to the symbol ADT and just show you that actually the goal of what we wanted to prove can be recast in terms of safe encapsulation of unsafe features. So I'll do that by introducing into my an unsafe assert expression. So here's the semantics of the expression. So assert E, it expects that E is a Boolean, and it evaluates E to a value, and if that value is true, then it just returns true. And if that value is false, well, you don't see a rule there, do you? Because in fact, it gets stuck. Okay. So this is by our definition of undefined behavior meaning getting stuck. Assert is a potentially unsafe operation. You only want to call it. You only want to use assert E if you know that E has to evaluate true to true in all programs. So with that in mind, we can now revise the code in symbol ADT to instead of just checking that S is less than star C and returning the Boolean, it'll actually do an assert here. And the point is that our goal, right, was to show that this check function always returns true. That's equivalent to the claim that this unsafe assert expression in this ADT has been safely encapsulated, meaning no well-typed client of this code can ever get it to get stuck. Okay, and so we can see that basically the problem with abstraction and the problem with not describing safe encapsulation of unsafe features are one and the same. So, summarizing, what we want is a stronger type soundness theorem that actually tells you what it means for a language to support data abstraction properly and tells you what it means for unsafe code to be safely encapsulated. And such a theorem exists. It's called semantic type soundness. And it's actually it's an idea that's been around for a very long time. I'm going to start by telling you about the high-level idea of semantic soundness and the basic proof structure for how you establish semantic soundness first, and then I'll get into more details about how you actually prove it and what are the challenges in proving it. So the high-level idea is pretty simple. We start with syntactic typing. That's your syntactic typing judgment with a single turn style. And the problem was, that syntactic typing can't account for terms E that use unsafe features. So the idea is to generalize to a semantic notion of typing, which I'm going to write with a double turn style. And the intuition is that this semantic notion of typing is more generous. It accounts for terms that behave safely when used at the type A, even if syntactically they use features that are not well typed. And so that's the intuition about semantic typing. Let's see how it actually plays out. So the semantic type soundness theorem is to establish that the semantic typing judgment satisfies the following two properties. The first one is adequacy, and that's just showing that if E is a closed, executable, semantically well-typed program, then it's safe to execute, meaning it won't get stuck. Okay, and intuitively, this is actually very similar to, this looks kind of like the way you state the syntactic soundness theorem as well, except now with the assumption that E is semantically well typed. It turns out, however, with semantic typing, adequacy is almost trivial, because the way you typically formulate the semantic typing judgment, you basically bake adequacy into it. So that's not going to be too interesting. What's much more interesting is compatibility. So compatibility says that the semantic typing relation is compatible with the syntactic typing rules of your language. And to explain more clearly what that means, it's easiest to look at examples. So basically, for every typing rule of your language, right, this is one typing rule for function application, you want to show that if you replace all the single turnstiles with double turnstiles, then the rule is still sound as a lemma. In other words, the premises of this rule imply the conclusion. And what are the consequences of proving this? Well, the first one is that there's a very simple corollary that's trivially provable by induction on derivations, which says that syntactic typing then implies semantic typing. And so this means that the semantic type soundness theorem gives you as a corollary syntactic type soundness, right? Because syntactic typing implies semantic typing. By adequacy, semantically well-typed programs are safe to execute, so syntactically typed programs are as well. But the point of doing it this way is that it gives you a more general framework in which to talk about encapsulation of unsafe code. And so to illustrate that, let's go back to this picture I had before, right? So you have all this code in the middle that's safe, and you have these libraries that use unsafe features. And the point is that now with compatibility in hand, we know that the whole program will be semantically well typed if all the pieces are, because semantic typing is preserved under linking. So that means if we want to verify that the entire program is semantically well typed and therefore safe to execute, we just have to verify semantic typing of all the pieces. Now, for all the safe code, we know it's syntactically well typed. So therefore, by the corollary on the previous slide, you know it's semantically well typed by construction. So there's nothing else to show there. For each of the libraries that uses unsafe features, you do have a manual verification burden, which is to prove that it's semantically typed at its interface type. Okay? And that is potentially difficult. Okay? That could involve an arbitrary amount of verification effort, because these libraries could use unsafe features in an arbitrarily subtle way. But at least you now, with semantic typing in hand, you have a verification condition against which you can verify the safety of these libraries. So that's the story about how semantic typing works at a very high level. There has been, as I said, this is not a new idea at all. There are many papers about semantic soundness from the past. I want to just highlight, just for purposes of time, I just want to highlight 3 papers that are relevant to what I'm talking about in this talk. So first one is Milner's original paper that I already mentioned, right? So Milner's original paper on type soundness was a semantic type soundness approach, and he used a logical relations model, what's called a logical relations model. I'll show you in more detail what that is in a few minutes. They're based on denotational semantics. There was quite a bit of follow-on work to this, but basically the short story is the denotational approach he was following didn't scale easily to richer type systems, even as rich as standard ML from the 90s, for example, because denotational methods had a very hard time dealing with, in particular, the feature of higher order state. So in other words, references to arbitrary values, and other features as well. But that was one of the key stumbling blocks. One of the breakthroughs, in my opinion, in this whole area was a paper by Andrew Appel and David McAllister from 2001, which introduced something called the step index model. This was also a logical relations model, but instead of being based on denotational semantics, it was based on operational semantics, and B, it sidestepped some of these problems with higher order state or with sort of recursive features in general by indexing the structure of the model over steps of computation. And the real benefit of that is that idea, although in that paper they only explored it for recursive types, the idea scales to much, much richer features, including higher order state and concurrency and control effects and many things very nicely. In her PhD thesis, Amal Ahmed explored that path, and she showed how you could scale the step index model up to handle higher order state using something called recursive Kripke structures. I'm not going to talk at all about all that sort of model theoretic stuff, but the point is that idea had a lot of legs, and there's been a huge amount of follow-on work on her thesis work. So you might wonder, if there's been all this work, why isn't everyone proving semantic type soundness results? Why is everyone still proving syntactic soundness results? And I would argue that the answer is best summed up by this slide. So this is the compatibility lemma for function application For a language the proof of the compatibility lemma for function application, the one I showed you a few slides ago, for a language very similar to my language, actually a little simpler, it doesn't have concurrency in it. This particular proof here is taken from Amal's thesis, but in my earlier work on step index logical relations, I had a number of papers with very similarly complex proofs. And so, if your reaction to this slide is fear and abject horror, then I would say you're like a normal, healthy person. You should pat yourself on the back. Yeah, because if you look at the details here, it's just scary, right? You have all this step index arithmetic, all this sort of k minus j minus I, and all this talking about store typings, and you're wondering why is there all this stuff about store typings and step index counting and approximations and stuff when all I'm talking about is safety of function application. Now, when I started out in this topic, apparently I wasn't a normal, healthy person because I saw this proof and I said, yeah, this is cool. I can prove really cool things with this. So I'm strange, but the turning point for me was actually when I visited Cambridge in 2008, and I gave a talk on some work, the initial work that I was doing with Amal and Andreas Rosberg on step index logical relations, and had proofs like this. And I met with Peter Sewell, if there's ever a man to burst your bubble, it's Peter Sewell. I sat down with him, and he's no stranger to complexity, but he looked at this and he sort of sighed and he said, and I'll do my best Peter Sewell impression. He said, "There must be a better way," and that sort of rang in my ears for a while, and because I was of course annoyed, but then I realized he was right, and the reason he was right is that if you actually, jumped the gun. The reason I realized he was right is that if you look at these proofs, if you actually get used to doing these proofs, you see that the high-level intuition, there's very good high-level intuitions behind this mess, okay? But they're kind of obscured in low-level details. And so, we're PL people. We know that if you have high-level intuitions that are getting obscured in low-level details, you should develop a higher-level language, or in this case, a higher-level logic that lets you do these proofs more easily. And that's what we've been doing for the last several years, my collaborators and I, in a project called IRIS. So IRIS is a logical framework implemented in the Coq proof assistant that's designed for reasoning about higher-order imperative and concurrent programs, improving deep properties of these programs, and it lets you do that kind of reasoning at a much higher level of abstraction than is available in other tools. There have been a number of applications of IRIS, and it's actually not. It's a very general tool. It's not designed for reasoning about one language. It's actually language independent, and so we've used it to reason about things like weak memory consistency, session types, Haskell, ML-like languages, Rust. So the first two lines there are papers that we have in POPL this year that are fundamentally using IRIS to do reasoning about both relational reasoning and semantic soundness proofs. So in this talk, I'm just going to focus on how you use it to do semantic soundness, and to sort of give you to pique your curiosity and get you interested in learning a bit more. Of course, this is all formalized in the Coq proof system. I forgot to mention. To pique your curiosity, remember this slide. That's how it looks like on paper. This is how it looks in IRIS in Coq. Okay, so normally, when you go from a paper proof to a mechanized proof, the rule of thumb is that the proof blows up an order of magnitude. But here the proof is shrunk by an order of magnitude, and it's actually not even. It's not because you might think it's because of some fancy proof automation or proof search. It's not. There's some good tactic engineering that is some very good tactic engineering that's behind this, but the proof boils down to a few applications of basic proof rules of the IRIS logic. And so hopefully you look at this and say, well, I mean, obviously shorter, but hopefully you say, this is something I could actually possibly pick up and try to use. So in the rest of the talk, I'm going to try to give you a very brief flavor of how this works. Okay. So I'm going to try to give you a flavor of how you can use IRIS to reason about semantic soundness for MyLang. Okay. I'll start by defining what semantic typing, defining a notion of semantic typing for MyLang. I'll then go and prove the compatibility lemma for function application, which is, as you saw already, very easy. And then I'm going to show you how you can prove that the symbol ADT that we saw before is semantically well typed, and therefore has been the assert expression in there has been safely encapsulated. So let's begin by defining semantic typing. This is the thing we want to define. For simplicity, because I have to sort of cut away material to get this talk done in time, I'm going to ignore the general case where gamma is non-empty and just consider an empty gamma. This is just for purposes of presentation. It's very easy to define the general one by closing substitutions. And I'm going to write this semantic typing judgment in this way. So I'm going to say little e is in the relation or the predicate defined by big E of A. Okay? And this is really just notation that I'm using in this talk to represent what in Coq you would write as big E of A applied to E. Right? So big E of A is here a predicate on terms in Iris. So how do you define this thing? That's it. That's the whole definition. I'm going to work through this definition and show you step by step what's going on. But hopefully you look at that and say that's not too bad. It fits on one slide with a reasonable font that you can actually read. So what's going on? Well, the first things first is that there's these deltas that just magically appeared on the slide. So I just wanted to point out, don't be afraid of the deltas. I'll come back to those later. That's for dealing with existential types. The first thing is, what is the definition of the big E relation? So this is basically the idea is little e here is semantically well typed at A. That's how we can read this predicate on the left. If and then the definition here is a Hoare triple. Okay, so that's your first indication that Iris is in fact a Hoare logic. In fact, it's a higher order Hoare logic. Okay, what does that mean? So it's a Hoare logic that's geared towards reasoning about higher order imperative programs. And the main proposition that we work with in logic most of the time is something is a Hoare triple. Okay, so Hoare triple PEQ has the following meaning: if P holds of the initial program state, then little e is safe to execute, and if E evaluates to a value V, then Q holds of the value. Okay, so the thing to note here is that this is somewhat different from the normal presentation of Hoare logic because it's done in functional style, meaning that the postcondition is not just a proposition but a predicate on the result value of the expression. Okay. Hoare triples in Iris are first-class propositions, meaning they can be nested. You can put them inside the P's and Q's, and that's important when you want to give specifications for higher-order functions. And Iris also supports higher-order quantification in the style of higher-order logic. Just to show you an example of a rule, I'm not going to really show you rules in this talk because I want to just give you a flavor of what it's like to work with it. This is the bind rule. This is a rule we use all the time. And this is basically a generalization of the standard Hoare rule of sequential composition. So the one on the top is the standard Hoare rule, where you say you verify C1 semicolon C2 by just verifying C1 and then C2, but where you use the postcondition of C1 becomes the precondition of C2. In Iris, we have a sort of functional version of this, where the term gets split up, the term that you're verifying gets split up into an evaluation context K, and the term that's in evaluation position E, and then you verify E and you verify K. Okay? And the postcondition of E becomes the precondition of K. So the only difference is that here K actually takes an argument, which is the result value of E. So you have to quantify overall possible values V that satisfied Q. That's it. Okay? So this is just to give you a flavor of how this relates to normal Hoare logic. In addition, Iris is a separation logic. Now, this is not actually that important for this talk, for the examples I'm showing in this talk, but it's important to mention because it's fundamental to the whole setup. So Iris builds closely on O'Hearn's concurrent separation logic from 2004. So it has the standards features you expect from separation logic if you've seen talks on separation logic in POPL before, like the points to assertion, X points to V, and P star Q for separating conjunction. Why do we use separation logic in modeling? Why is this useful in modeling type systems? Well, number one, if you're modeling something like Rust, which has a substructural or ownership-based type system, then this is a perfect fit because the language you're modeling already has notions of ownership and separation in it. So it's very useful to have those notions also in the modeling logic. But it's also very useful even just in reasoning about standard structural type systems like MyLangs. Because ultimately, at the end of the day, we want to verify the safe encapsulation of some libraries when they're linked with arbitrary well-typed code. And that means you have to reason modularly. And if you're going to reason modularly about state, then separation logic is an excellent foundation. Okay, so back to the logical relation. So what does this say? It just says that under E is semantically well typed if under at A, if under trivial precondition, E is safe to execute and produces a value that's related by that satisfies the value the predicate V of A. Okay, so V of A is the logical relation defining semantic typing on values. And now I can quickly work through most of this relation there's going to be just a few interesting things. So let's work it case by case. So this relation is defined inductively on types. In the case of base types, semantic typing coincides with syntactic typing, so there's nothing interesting there. In the case of product types, V semantically inhabits A cross B if it's a pair, V1, V2, and V1 is semantically well-typed at A, and V2 is semantically well-typed at B. Okay, so again, pretty straightforward. Function types is interesting, but also should be intuitively clear. So the idea is that when is V a valid or semantically well-typed at A arrow B? Well, it's semantically well-typed if it's safe to use it at that type. And what does it mean to use a function? You apply it. So if for any argument U that you pass in that's semantically well-typed at A, then you can prove this Hoare triple, which says the result of V applied to U will be semantically well-typed at B. And you'll notice here something interesting, which is that we have a negative or contravariant occurrence of the big V in its own definition. Again, this is okay because we're defining the entire predicate by induction on types. So A and B here on the right-hand side are smaller than A arrow B on the left. All right, now we get to an actually somewhat more interesting case if you haven't seen parametric models before. So this is the case for existentials. And the thing that's interesting here, right, so let's just walk through it a little bit. So when is V a valid, a semantically valid thing at type exists alpha A? Well, first of all, it has to be an existential package, pack BU as whatever. And so you might expect that, so B here is the type witnessing alpha internally, and U is the implementation of the operations of the existential package. So you might think, if you haven't seen this kind of thing before, that that U should be semantically well-typed at A, where you plug B in for alpha. But actually that doesn't quite work because what you really want to do is you want to be able to pick an arbitrary instantiation of alpha. You want to give it an arbitrary meaning. So in other words, we want to be able to pick some T, some arbitrary iris value predicate that we're going to use to represent the abstract type alpha. And that will allow us to impose an invariant on the meaning of the abstract type. If you've seen parametric models before, this is like the totally standard thing. If you haven't, well, we're going to see an example shortly. So yeah, you say there exists some T such that U is semantically well-typed at A, where you extend, and now here's the deltas come in, where you model alpha as being this predicate T. And this explains why we need the deltas. This is just for, we need to thread through this interpretation of the free type variables of the thing we're interpreting, of the A. Okay. Correspondingly, in the variable case, you need to say when is V semantically well-typed at alpha? Well, it's just when it satisfies the predicate delta of alpha. Okay. And the last case is references. So when is V a valid reference? When is it semantically typed at ref A? Well, so this is the first thing where we actually have an interesting logical connective you probably haven't seen before, which is this box thing, and that's an invariant. So this is a feature also derived. It's a variant of a feature in concurrent separation logic, resource invariance. The idea is that this P inside a box means that P has been established as an invariant. Okay, and we'll see how to work with that in a few minutes. So what is the invariant here? It just says V is well-typed at ref A if there's an invariant that says that V always points to some value U such that U is well-typed at A. Okay, that value might change over time, but it's always going to be something that is well-typed at A. Right? And that's the whole thing. All right, so we've seen the entire definition. One technical point that I need to explain before I move on is that there's an important distinction in iris between two kinds of propositions that I've been glossing over in this presentation so far, and that is between what we call persistent and ephemeral propositions. So by default, separation logic propositions are ephemeral, meaning that they can change, their truth can change over time. So right now, at this point in the program, maybe x points to 4, but after a few steps of computation, then maybe x points to 5. Okay. By contrast, a persistent proposition is a fact. Okay, so this is something that once it holds forever. And there's various nice properties that persistent propositions have, such as they're duplicable, unlike ephemeral propositions. So P equals P star P, and conjunction and normal conjunction and separating conjunction coincide on these things. So the reason I'm bringing this up is that this logical relation on values has to be persistent. because we may use the fact that a value has type A many times in our reasoning, right? Values can get substituted for variables, and variables can appear an arbitrary number of times. So, so you need to ensure that this logical relation on values is persistent. And fortunately, there are many different kinds of persistent propositions in Iris. One of them is so pure propositions, Hoare triples, those are facts. Invariants, once they're established, an invariant holds forever, so that's also considered persistent. And you can compose these things with various connectives. So the point is actually this logical relation is already persistent by construction with one caveat. So you'll see there's only all those there's Hoare triples and various other pure propositions and an invariant in the ref case. But one caveat is that we need to assume that the delta is persistent as well because it gets used in the variable case. And correspondingly, when we extend the delta in the existential case, we need to make sure that t is persistent. So we have to quantify over persistent t. Okay. So I just needed to explain that because if I don't have the persistent t there, it's not correct. Okay, so I want to very quickly walk through a compatibility proof and then also show you that the symbol ADT is encapsulated. So here's the lemma. This is the thing we want to prove. I'm again going to simplify and just look at the case where the gammas are empty. This is really not much of a simplification. And what does it boil down to? Well, to show you how this proof works, I'm going to try to give you the flavor of how this works when you do this in the Iris proof mode in Coq. So I'm going to sort of present this in a more interactive style. And when you work in Iris proof mode in Coq, you actually have two kinds of contexts, or two kinds of preconditions, a persistent one P and an ephemeral one Q. And so this is the format in which I'm going to show these proofs in this last part of the talk. So that's the theorem. That's the form of these the statements I'll be proving. And in this case, what do I want to prove? I want to prove that if E1 is semantically well typed, I just unfolded the definition there, and if E2 is semantically well typed at A, then the application will produce a value that's semantically well typed at B. So how do we do this? Well, fortunately, I've shown you the one rule you need in order to do this proof, which is the bind rule. Right? We know that we have some specification for E1, and E1 is the thing that's in evaluation position in this term. So by using the bind rule, you knock out E1, you bind some variable V1 to represent the value you got from E1, and now in your persistent precondition, you know that that V1 you're quantifying over is semantically well typed at A or B. And now, of course, V1 is a value, so the next thing in evaluation position is E2. So we can apply the bind rule again. The same exact thing happens. And we now learn that this V2 that's universally quantified is semantically well typed at A, and we just have to show that V1, V2 is in is semantically well typed at B. Well, you just unfold the definition of the logical relation at A arrow B, and that tells you exactly what you need. Okay. So I wasn't lying when I said that the Coq proof that I showed earlier was really just applying the rules of Iris. If you look back at the proof now, you see, okay, you can ignore the I intros. That's just putting things into the initial context. We have two applications of the bind lemma for two different contexts, two different evaluation contexts, and then you just unfold the definition of the logical relation at the arrow type, and that's it. Okay, so really this is a manual proof, and yet it's so much simpler. And you might wonder, why is it so much simpler? It's simply because Iris hides all that step index stuff, right? That stuff is just buried inside the consistency proof of Iris, the model of Iris. So the user of Iris doesn't have to worry about it. Okay, so now I want to get to the last bit, which is proving that this the symbol ADT is safely encapsulated, that it's semantically well typed. So this is a more interesting proof, obviously, because this requires some cleverness. Okay, not really cleverness. So what is the example? Right, this was the symbol ADT. We want to show that it's semantically well typed. We have to show it's in the E relation at its existential type. So putting this into our proof framework, what do we have? We have that there's the term on the upper right, and we have the postcondition on the lower right. So let's just do the first step of computation, right? That we can do the first thing to evaluate in this term is allocating a fresh ref cell for C. So we can allocate that by just symbolically executing. This is a simple proof rule in Iris. And now we have in our ephemeral precondition that C points to 0 for some C. For some C. So now the problem is, in order to do the rest of the proof, we really want to impose an invariant on C. But it's not obvious what is the right invariant to impose, because what can we say about C? Well, it could be, at any point in time, it could be any natural number. Okay, that's not useful. So the trick here, and this is where I sort of introduce something magical, because I only have so much time. The magical thing I'll introduce is ghost state. Okay. So if you've ever used ghost state, if you ever used Hoare logic before, then you're used to the idea of ghost state. Right? This is a very common idea in Hoare logics from the very beginning. It basically is just auxiliary logical state that's used in proofs to encode things that are logical state of the proofs, but not physical state of the program. So, for example, trace information or permissions or things like that. And it's traditionally represented by just sort of a ghost set of variables. But in Iris, you have a more general mechanism that allows users of the logic to pick their own user-defined, customized, structured forms of ghost state. In other words, theories of ghost state that are appropriate for the proof you're doing. And that sounds all very vague, so let me make this concrete. Here is the ghost theory that we want to use to do this proof about the symbol ADT. It says, I'm declaring, okay, and this is the magical part, that there is a counter predicate and a symbol predicate, and some axioms about these things. And let me explain what they are. The counter predicate says the counter is currently n. And so you can think of this as mirroring the physical state, but just in this ghost state level. Right? So this is an ephemeral proposition. The symbol predicate is saying n is a valid symbol that has been generated so far. And symbol, unlike counter, is persistent because once something is a valid symbol, it remains a valid symbol forever. And then there's three of these. There's three things you get. You learn about counter and symbol. The first one is that ownership of the counter, you're getting ownership of the counter at 0, right? That's your initial state, is that the counter starts at 0. And then you have two axioms for actually reasoning about it. The first one says we can bump up the counter from n to n plus 1, at which point n becomes a valid symbol. So it says that if the counter is currently n, we can do a state update, a ghost state update move, that moves it to n plus 1, and at that point we learn that n is now a valid symbol because it's less than the current value of the counter. Okay. The second axiom says that all valid symbols must be less than the current value of the counter, right? So if you own counter n and you also know that s is a symbol, then it must be that s is less than n. Okay? And this corresponds to the intuition that you have when you're writing the code about the logical moves that happen as you sort of symbolically reason about your code. So now let me just quickly show you how this plays out in the proof. Right? This is going to be a pretty breezy proof by animation, but you have to believe me that if you actually do this in Coq, and you can look on the Iris project webpage and see the proof of this in Coq, it plays out exactly like this. So the idea is, first of all, we're going to use that ghost theory I just introduced, and by the way, I'll get back to why is that a reasonable thing to do at the very end. We'll introduce that ghost theory. That ghost theory, we get counter 0, and now we want to actually introduce our invariant. So what is our invariant? Well, obviously it's not that c points to 0. We want to generalize this to say that c points to some n, and whatever n that points to, it should be the same one that the ghost state predicate talks about. So once we've done this, once we've weakened that precondition, we can now allocate an invariant. So move it into the persistent context and put the box around it. So this means now this property must hold forever. And now we're ready to actually do the rest of the proof. So the first thing we want to do is actually pick the interpretation of the abstract type alpha in the existential. And remember, the idea here was that we get to pick an arbitrary interpretation of alpha that represents what symbols are supposed to mean. And what can we pick? Well, we'll pick t. We have something right on hand to pick for this t. We'll just pick the symbol predicate, right? We want alphas to represent symbols. Define alpha to be symbol. Okay, that's it. So our proof obligation then becomes that we want to show that the operations are logically well-typed or semantically well-typed, where alpha is mapped to symbol. All right. So now let me show. I'm just going to show you the case, the first case, because I'm running a bit short on time. So the idea is we have this fetch and increment, right? So this is a lambda. To show that this is in unit arrow alpha, this basically boils down to just showing that the body of the lambda, the fetch and increment of c, produces something that's semantically well-typed at alpha. And how do we prove this? Well, we've established this invariant, so we can now open the invariant and use it. So let's use the invariant. And the way you do that is simply by temporarily moving it into your ephemeral precondition. And now we can work with it during the execution of this fetch and increment, as long as we restore it at the end. So and we know that c points to n, so we can perform the fetch and increment. And what will that do? It'll give us that C points to n plus 1, and the term now is just n. Now our precondition is out of whack because C is pointing to one thing and the counter is talking about another. So this is where we have to use that counter update rule for the from the ghost state theory to update counter n to counter n plus 1. And so counter n goes away, and counter n plus 1 and symbol n show up. So now we know that n is a valid symbol using that rule. And now our ephemeral precondition is in good shape. We've restored the invariant, so we just have to we weaken it back into the invariant form, and then we restore the invariant. And now we just have to show that n satisfies the postcondition. Well, what is the postcondition? It's really just symbol, right? We just have to show that the result of this thing satisfies the symbol predicate. And we, of course, know in our persistent precondition that n is a valid symbol. Right? So that's all. So in the end, it's actually not that hard once you set up, once you have that ghost theory in hand. So I'm going to skip ahead because I'm short on time here. But basically, all that happens in the next, in reasoning about the other operation, is you use the same thing. You use the fact that you've set up this invariant, and you just directly apply that other axiom that said that if n is the current counter and s is the symbol, you know that s is less than n has to be true. So this assertion must hold. Okay, but that's just applying this ghost axiom we had. So that's the end of this proof, and I'm out of time now. So I just want to briefly say, why was that a valid move, the one I made in the middle of the proof, right? I did this tricky thing where I just introduced this ghost theory out of thin air, and why is that actually consistent to do? Well, the good news is Iris has a very good story for this. There's a very general approach to how we derive the consistency of these ghost theories. We basically just model the ghost state using some kind of PCM, which is a partial commutative monoid. If that sounds like some mumbo-jumbo, really that's just the standard way you model separation logics. And so this allows you to sort of give a non-standard model of separation logic that's appropriate for your theory of ghost state. And then once you've done that, Iris gives you two primitive proof rules. They're really very simple. Again, my point here is that none of this is really that complicated. And using those proof rules, we've been able to derive the consistency of many different ghost theories that are appropriate for different kinds of applications. If you come to Ralph's talk on Friday, for example, about our Rust Belt project, you'll hear a bit about the lifetime logic that we've derived in Iris for reasoning about lifetimes in Rust. That's yet another one of these ghost theories, and we use that logic to verify the soundness of many different Rust libraries that use unsafe features. So to conclude, good type systems support data abstraction and safe encapsulation of unsafe features. Syntactic type soundness just doesn't tell you whether a type system is good in this sense. Semantic type soundness does, but it's been quite complicated to prove in the past. And now, using Iris, I would argue you can really prove this for real languages. And I hope that I've given you the impetus to go out and try it, download it from the Iris project website, and give it a whirl and give us some feedback on how it's working. And I want to thank all my collaborators on Iris and on logical relations research over the past 10 years, and all my other collaborators who've made my research and my life so wonderful. Thank you.
There's a microphone right there. Dave.
So first off, let me say that is one of the best invited talks I have ever seen in my life. Congratulations, totally amazing. The second thing, do you have a tutorial paper that I can go over to with my graduate students to learn this technology and apply it?
We're working on it. We have a tutorial documentation that was developed by Lars and his postdoc Alish. That's quite significant now. It's about 100 pages. That's a starting point.
I'd like something shorter than 100 pages on my lab.
You want something shorter than 100 pages? Oh.
Yes.
There's papers that are shorter than 100 pages, but I don't know that they're the best tutorial documentation. It's something we're working on.
You can do it. I know you can.
But, yeah. No. It's totally on our radar. It's totally on our radar. We're actually planning to meet the Iris developers this week to discuss how to make.
So if I have one actual question. So if I had one perhaps naive critique, it is that the syntactic type soundness theorem can be nicely encapsulated with two top-level statements of progress and preservation. But it didn't look to me like your definition of compatibility could really be encapsulated with a closed form top level statement. You said, please go and replace all of my typing rules.
It's not. It's a bunch of lemmas corresponding to each of the typing rules of the language. So it's really dependent on your particular language what that statement is.
Right. So I find that slightly dissatisfying, and please improve it in the next 10 years. Thank you.
Before the next question, a quick announcement. Can you just ask the speakers for the lightning thing to line up somewhere there?
Can the speakers for the lightning thing line up somewhere around there? That means you who are in the... Yeah.
Go ahead.
Oh, just one thing to mention, which is new Perl. Because
Yes.
the whole idea of new Perl since
Yes.
1980 was computational type theory, which you're calling semantic type theory,
Yes.
in which the typing is defined by evaluation, it's defined by the behavior of programs,
Yes.
and you build up the program logic as an arbitrary thing that you do for pragmatic purposes and show that it happens to be sound. And moreover, the theory is designed not to accept Church's law, so that in particular it's open-ended and compatible with all sorts of extensions, foreign functions, everything fits completely into that framework. So the gap in your history in the 1980s and 1990s and 2000s.
That should have been. It should have been hopefully clear that something happened between 1978 and 2001. I could only say so much in this talk, but yes, the reason I focused on those three things was simply that you need to get into the step index stuff in order to be able to build the models of the languages.
Yeah, that's a nice advance, but it's nice if you're doing a historical survey. It's nice to mention that. But I will also say computational type theory is alive and well and living at Carnegie Mellon, amongst other places at Cornell.
Yes, it is.
So I'll mention that. Okay, see.
Once an advisor, always an advisor. Adam, yeah.
So we're used to thinking of a distinction between safety and functional correctness, and it sounds like you're saying type systems which are used to applying to prove safety, we should be asking more from to prove elements of what we usually call functional correctness. But at the same time, the particular type system you showed us isn't nearly strong enough to formalize all the contracts we'd associate with functional correctness. So what really is the advice you're giving us?
The advice I'm giving you is to prove semantic soundness. I mean, I think the point is that, yes, you do need to think in terms of verification, right? I mean, types are all about enabling verification. It's making modular verification possible. And so that's all I'm really saying. And that if you want to show that your type system is doing that, you have to prove something like semantic soundness.
But you could have a type system.
But I agree completely. You want some stronger verification as well.
You could have a type system and a separate correctness proof system, and you could trade off complexity between those two, and it's not obvious what's the right way to divide that work, right?
Let's take this offline.
Okay.
One last question. Oh, Ron.
All right, covfefe. So where do things break down when you try to add covfefe to the system? I mean, I'm hoping that they would break down because that would destroy the invariant that you talked about, right?
Right.
So
yeah. Okay. Hold on. Well, where do they go? Where do they break down when you get to? Let me just show the covfefe thing here. Right. So where they break down is the covfefe will not be semantically typed at unit. Right. If you try to reason about the case where it modifies some random thing in memory, that's going to be possibly breaking some invariant that's been placed on the location.
So would
null.
like the compatibility lemma would that break? Or
yeah, I mean that would be the thing, right? If you had to add this to your type system, then you'd be wanting to show that covfefe is semantically well typed, right? Replace the single turnstile with a double turnstile, and it's not because it could break some invariant that's imposed on L. Right.
Cool.
In Iris, right, there could be some invariant that someone created in the proof that talks about L, and changing n to 0 could break it.
Thank you.
Okay, let's thank Derek once again.